Section: Introduction. In this section, we discuss our exploration of reinforcement learning, which has seen impressive achievements in games like chess, Go, and poker through imitation learning and self-play. However, these methods often demand extensive training and engineering tailored to specific tasks. In contrast, large language models, LLMs, act as generalist agents, showing strong capabilities across various fields. They can utilize existing knowledge of game strategies and adapt to new scenarios without needing extra training. Despite their potential, recent research points out that text-based language agents often struggle with planning and can fall short compared to traditional heuristic bots in games, sometimes failing to understand basic mechanics. To address these issues and further explore LLMs in complex gaming contexts, we focus on Pokémon Battles, a fast-paced and strategic two-player game. Pokémon Battles are particularly challenging for AI, featuring over 1,000 unique Pokémon, each with distinct abilities and stats, leading to an enormous state space complexity. The game also has partial observability, where we gradually learn about our opponent's team during play, complicating the search space throughout the match. Additionally, battles can last from 6 to over 100 turns, making it impractical to explore every possible move. We propose that having a well-informed prior can help narrow down the Minimax search to human-like strategies. LLMs, trained on diverse datasets that include Pokémon information, provide a solid foundation for this approach. Our goal is to create an agent that can suggest strategic actions, accurately model opponents based on their history and team, and evaluate game trajectories. To achieve this, we introduce PokéChamp, a language agent that performs at a human expert level in Pokémon battles. PokéChamp uses a large language model to enhance the Minimax tree search by integrating LLMs into 3 key areas: sampling player actions, modeling opponents, and estimating value functions. This allows us to effectively use gameplay history and human knowledge to manage the search space and deal with partial observability. In our framework, the LLM acts as a black box, giving us the flexibility to choose any model based on our resources. We do not require additional training on Pokémon data, relying instead on the LLM's existing knowledge and our innovative integration with game theoretic planning. We also developed a world model to simulate game transitions and tackle the challenges of partial observability and complex mechanics. This model includes a one-step look-ahead to compute game dynamics and uses historical data to estimate opponent stats. Our dataset, containing over 3 million Pokémon battles across various skill levels, serves as a valuable resource for modeling opponents and developing strategies. We evaluate PokéChamp through a series of experiments against established Pokémon bots, including heuristic-based and state-of-the-art LLM-based agents. We assess its performance in 2 game modes: Generation 8 Random Battles, which test adaptability, and Generation 9 Overused Meta, which examines strategic depth. To further validate PokéChamp, we compete against human players in online ladder battles, revealing its effectiveness against skilled opponents. Our results show that PokéChamp outperforms existing bots, achieving a 76% win rate against the strongest LLM-based bot and an 84% win rate against the top heuristic bot in the Generation 9 Overused Meta. Notably, using the open-source 8 billion parameter Llama 3.1 model, PokéChamp consistently wins 64% of the time against the previous strongest LLM-based bot, GPT-4o, demonstrating the strength of our approach even with smaller models. In online ladder battles, PokéChamp achieves an expert-level ELO rating of 1300 to 1500, placing it among the top 30% to 10% of competitive players. This performance highlights our agent's capability to compete effectively in a dynamic, partially observable environment. Additionally, we present several advancements that broaden our research's impact. We introduce the largest Pokémon battling dataset to date, with over 3 million games, including more than 500,000 high ELO matches, offering a unique resource for analyzing competitive strategies. We also create a series of benchmarks based on real player data and crafted puzzles to rigorously evaluate battling skills. Furthermore, we enhance the local game engine for better accuracy and performance, ensuring reliable simulations of official battle mechanics. Through PokéChamp, we showcase the potential of combining LLMs with game theoretic planning to achieve expert-level performance in complex environments without task-specific training. Our work paves the way for future research in competitive multi-agent settings and advances AI capabilities in strategic gameplay. Section Summary. In this section, we discuss the development of PokéChamp, a competitive language agent that leverages large language models, LLMs, to achieve expert-level performance in Pokémon battles, a complex and partially observable game. By integrating LLMs with game-theoretic planning algorithms, we demonstrate that PokéChamp can effectively model opponents and propose strategic actions without requiring additional training, outperforming existing AI agents and achieving high win rates against both heuristic bots and skilled human players. Section: Related Work. In this section, we discuss related work in competitive games. Previous research in games like chess, Go, poker, StarCraft 2, and Dota 2 has utilized reinforcement learning to achieve superhuman performance through extensive training from scratch. Other studies have tackled competitive fighting games, such as Street Fighter, using multi-agent reinforcement learning in a tournament format where AI agents compete in one-on-one matches. This approach has led to human-level performance in more realistic simulations, like Gran Turismo Sophie, which surpassed top human drivers in Gran Turismo Sport. Some attempts have also been made in Pokémon battles, showing competitive results against basic bots and achieving human-level performance through iterative learning and reward optimization. However, unlike these previous efforts, our method, PokéChamp, does not involve exhaustive training of Pokémon and still performs at an expert level without explicit training. We also note the rising interest in language agents for games, though they still struggle with basic planning tasks. For instance, large language models, LLMs, cannot effectively play the Nash strategy in tic-tac-toe, a simple game that has been solved. This highlights the need for better planning capabilities in LLMs. In the roguelike game NetHack, an LLM-based agent performs poorly compared to a more advanced heuristic bot. Other research has employed prompting techniques to help LLMs overcome planning challenges in games like Pokémon and StarCraft, as well as in mixed cooperative competitive games like Avalon. Additionally, LLMs are being tested in open-world games, such as Voyager in Minecraft, which learns skills by reading strategy guides. Some LLMs have been fine-tuned using human game data in games like Diplomacy, and there is growing interest in using reinforcement learning and model distillation to enhance LLMs. We have seen significant improvements in reasoning capabilities of LLMs through advancements in prompting and planning techniques. For example, chain-of-thought prompting provides step-by-step examples, while self-consistency sampling enhances performance by exploring multiple reasoning paths. The Tree of Thoughts framework allows models to evaluate various reasoning paths, and the React framework combines reasoning with text actions for better task performance. Other research has shown that language models can act as both world models and reasoning agents, particularly in the reasoning via planning (RAP) approach. The integration of search algorithms with language models, like the TSLLM framework, has also shown promise, applying tree search methods to guide model training. Furthermore, researchers are exploring reinforcement learning techniques to improve self-correction in models, as seen in the SCORE method and the reflection framework, which enhance performance without extensive fine-tuning. Finally, we examine competitive Pokémon battling, which presents a complex environment with a large state space. In this turn-based combat, 2 players deploy teams of 6 Pokémon, with only one active at a time. Players can choose to attack or switch Pokémon each turn, and the game ends when all Pokémon on one side are defeated. The state space is vast, with an estimated number of possibilities for the first turn alone reaching 10 to the power of 354, due to over 1,000 Pokémon species with diverse types, stats, and moves. Players have complete information about their own team but only partial information about their opponents, requiring strategic decisions to be made under uncertainty. Team construction, or team building, is a crucial pre-battle strategy, where players select moves, abilities, items, natures, and specific distributions of effort values and individual values that affect Pokémon stats. The action space includes move selection, Pokémon switching, and game-specific mechanics. The transition function involves random elements like move accuracy and damage, while rewards are binary, indicating win or loss. The competitive metagame evolves as players discover new strategies, making adaptability essential. This complexity and partial observability make competitive Pokémon an excellent testbed for game-theoretic research. Section Summary. In this section, we review previous work in competitive games, highlighting the use of reinforcement learning to achieve superhuman performance in various games, including Pokémon, while noting the limitations of language agents in planning and reasoning. We also discuss the complexities of competitive Pokémon battling as a partially observable Markov game, emphasizing its vast state space and the strategic decision-making required under uncertainty, making it a valuable area for game-theoretic research. Section: Pokémon Showdown Platform. In this section, we discuss the Pokémon Showdown Platform, which is a popular online battle simulator that accurately reflects the official battle rules. It allows us to engage in battles without needing to breed or train Pokémon in-game, making it easy to experiment and compete. Showdown offers various battle formats, such as singles, doubles, and tiered formats that categorize Pokémon based on their usage and strength. Its accessibility and accurate game mechanics have made it essential for the competitive Pokémon community and a useful resource for AI research in complex gaming scenarios. We focus on Generation 9 Overused, OU, the most popular competitive format of the latest generation, which showcases the balance between diversity and strategy in Pokémon battles. The OU format restricts the use of overly powerful Pokémon while still offering a wide range of viable choices, leading to a dynamic metagame. It introduces mechanics like terrestrialization, allowing a Pokémon to change its type once per battle, which significantly impacts type matchups and strategies. The variety of possible Terra types for each Pokémon increases the complexity of the game, requiring us to adapt to a constantly changing environment of popular Pokémon and counter strategies, while also considering the new type changes from terrestrialization. Each player has a total of 150 seconds for the entire match, with a limit of 15 seconds per turn. If we exceed either time limit, we automatically lose, adding a layer of complexity that demands quick decision-making and prevents exhaustive strategies. We can model Pokémon battles as a partially observable Markov game, POMG, represented by a specific set of components. Here, the state space includes hidden states, while the observation spaces contain the information available to each player. The action spaces represent the choices available to both players, and the transition function describes the probabilities of moving from one state to another based on the actions taken. We define a POMG with a tree structure and perfect recall, meaning that for any state, there is a unique history of past states and actions leading to it. We assume the learner is the max player aiming to maximize rewards, while the opponent is the min player. In a Pokémon battle, a state includes the complete history of the game and both players' Pokémon teams, while an observation contains the player's team information and partial details about the opponent's team. A policy for the max player maps observations to action distributions, while the min player has a similar policy. The game trajectory over a set number of steps defines the value function for a pair of policies. The Nash equilibrium is a pair of policies where neither player has an incentive to change their strategy if the other player's strategy remains the same. In our context, the Minimax theorem applies, indicating that the Nash equilibrium also represents the optimal strategy against an adversarial opponent. This formalization captures the key aspects of Pokémon battles, including partial observability and the goal of maximizing expected rewards, setting the stage for our methodology. Section Summary. In this section, we describe Pokémon Showdown as an online battle simulator that allows players to engage in competitive Pokémon battles without the need for in-game preparation, supporting various formats like Generation 9 Overused, OU. We formalize Pokémon battles as a partially observable Markov game, POMG, detailing the structure, policies, and Nash equilibrium, which captures the strategic complexity and decision-making involved in these turn-based contests. Section: Minimax Agent and PokéChamp. In this section, we describe our Minimax Agent and PokéChamp, which uses a new method that combines large language models with Minimax tree search. We start by outlining a general framework applicable to two-player zero-sum games. Then we explain how we tailor this framework specifically for Pokémon battles. Our Minimax tree search framework focuses on pure strategies due to computational limits and the need for quick decisions. At each step, we observe an info set, choose an action, and the opponent does the same, leading to a new info set. We repeat this until the game ends, creating a tree where each path represents a series of actions and info sets. We receive a reward for each final info set, and the Minimax algorithm suggests the best action based on this process. However, the size of the tree increases rapidly with depth, making exhaustive searches impractical. To enhance performance, we introduce a Minimax agent framework that incorporates large language models into three main areas. 1. Player action sampling. We provide the LLM with essential information about the current info set and ask it to suggest a small number of possible actions, which helps reduce the search tree and computational costs. 2. Opponent modeling. We also use the LLM to predict likely actions from the opponent. This is more complex because the learner has limited visibility and must infer hidden states based on what they can see. 3. Value function estimation. Instead of expanding the search tree to the end, we limit it to a certain depth and use LLMs to evaluate the info sets at that point, replacing traditional terminal rewards. This is challenging with standard methods, but LLMs can effectively approximate value functions by utilizing common knowledge from gameplay. Next, we detail the implementation of PokéChamp and its three key modules. One challenge we face is simulating game transitions under partial observability. The learner only sees the current observation, not the hidden state. To estimate this hidden information, we use statistical data from Pokémon Showdown, including move pools and item usage, along with LLM predictions for opponent stats like attack and defense. We simulate the game to predict the next state, acknowledging that actual Pokémon games involve randomness, so we compute expected values to manage this complexity. For player action sampling, given an info set, PokéChamp generates potential actions to build the Minimax search tree. The input for this includes the overall team strategy, the observable state, battle history, and an approximate state transition heuristic to estimate the number of turns needed to defeat the opponent's Pokémon. We also consider legal actions available under the current info set, incorporating both LLM-generated actions and a few from our tools, such as the best move and switch choices. Section Summary. In this section, we describe PokéChamp, a novel Minimax agent that integrates large language models into the Minimax tree search framework for two-player zero-sum games, specifically tailored for Pokémon battles. We outline our approach to player action sampling, opponent modeling, and value function estimation, which collectively enhance performance by reducing computational costs and improving decision-making under partial observability. Section: Opponent Modeling. In this section, we address opponent modeling to tackle the challenge of not fully observing our opponent's actions and hidden states. We use a mix of historical data analysis and predictions from a large language model, LLM. For estimating unknown opponent statistics, we analyze past data to determine the likelihood of various stat distributions. This helps us approximate the true state based on our observations. The LLM also predicts likely actions from the opponent by generating responses based on prompts that focus on their perspective. Given the time constraints of live gameplay, we utilize an LLM-generated value function to evaluate potential moves in our decision-making process. The LLM scores possible actions based on positive factors like the effectiveness of current moves and the number of remaining Pokémon, as well as negative factors such as excessive switching and the strength of the opponent's Pokémon. We then determine the best action to take based on these evaluations. By integrating action sampling, opponent modeling, and value function approximation, we enable PokéChamp to effectively navigate the complex and partially observable environment of Pokémon battles, aiming for optimal play within real-time constraints. For evaluation, we describe our methods for assessing PokéChamp through both offline datasets and online games on the Showdown platform. We compiled a large dataset of over 3 million Pokémon battles, which provides valuable information for estimating transition probabilities and opponent strategies. This dataset includes detailed records of team compositions, move choices, and battle outcomes, forming a solid basis for our analysis. We also conducted experiments to evaluate our action prediction capabilities, focusing on predicting human actions from our dataset. This task is challenging due to the limited visibility of game states, as we often lack key information about player strategies. To overcome this, we reverse-engineered moves and team compositions from replay data and supplemented it with historical information. This allowed us to create a more complete picture for our predictions. Our results show that the accuracy of player predictions for PokéChamp ranges from 26% to 30% as LO ratings increase, while opponent predictions are lower, between 13% and 16%. This indicates that predicting opponent actions is more difficult due to limited information. However, our LLM predictions significantly outperform random guesses. We also noted that there can be multiple valid actions in many situations, so we included performance metrics for the top predictions, showing improved accuracy with more options. To further evaluate PokéChamp's decision-making skills, we developed game puzzles that test its understanding of game mechanics and ability to find optimal strategies. We created a benchmark of 1,000 one-on-one battle scenarios to assess how well PokéChamp can identify optimal move sequences. Each scenario was chosen to ensure a possible win condition, allowing us to evaluate its performance effectively. Our results indicate that PokéChamp achieved an 86% win rate, outperforming Pokémon, which had a 76% win rate, demonstrating our method's effectiveness in this constrained setting. Section Summary. In this section, we address opponent modeling by combining historical data analysis and LLM-based predictions to estimate opponent statistics and actions, while also employing an LLM-generated value function to navigate the complexities of Pokémon battles. Our evaluation methods, including a comprehensive dataset of over 3 million battles and targeted action prediction experiments, demonstrate that our approach significantly outperforms random predictions and achieves a higher win rate compared to existing methods. Section: Puzzles for Special Mechanics, Terastallization and Dynamax. In this section, we evaluate PokéChamp's ability to use specific game mechanics like Terastallization and Dynamax through developed puzzles. These mechanics add complexity to the game's state and action spaces. Our world model and prompting system help PokéChamp understand and effectively use these mechanics. The agent learns about the effects of these mechanics, and a one-step look-ahead allows it to anticipate different outcomes. For instance, we see PokéChamp switch its Pokémon after understanding Roaring Moon's new weaknesses post-Terastallization and use Dynamax to boost its health and attack power, leading to consecutive knockouts. These examples show how PokéChamp navigates complex game situations and makes strategic decisions. Next, we assess PokéChamp's performance in the Gen 9 OU format, which includes the Terastallization mechanic and custom teams. We compare it against other bots and real human players on the online ladder. Our experiments involve at least 25 matches between each method, totaling over 100 games for LO calculations. We pit PokéChamp against advanced bots and agents, including Pokémon, Abyssal Bot, One-Step Look-Ahead Bot, Max Power Bot, and a Random Bot. Notably, PokéChamp with GPT-4o achieves an impressive 84% win rate against the Abyssal Bot, earning an LO rating of 1268. Even with the smaller Llama 3.1 8B model, PokéChamp outperforms Pokémon powered by GPT-4o, showcasing our method's effectiveness. We also conduct mirror matchups without Terastallization to isolate its effects, revealing that team composition significantly influences performance, with PokéChamp winning 90% of those matches against Abyssal. To evaluate real-world performance, we tested PokéChamp on the Pokémon Showdown online ladder from September 1 to 7, 2024, facing human opponents in the Gen 9 OU format. Players have a time limit of 2 minutes and 30 seconds per turn, with potential extensions. About one-third of PokéChamp's losses were due to timeouts, but it achieved a 76% win rate in the remaining games, reaching an ELO score above 1300. If we exclude timeout losses, we estimate its ELO rating to be between 1300 and 1500, placing it in the top 30% to 10% of players. On March 3, 2025, we explored a faster version of our method, PokéChamp Fast, which dynamically chose between a one-step look-ahead or a truncated Minimax search. However, this variant's ELO performance ranged from 1150 to 1310 without stabilizing, which is lower than our standard method. We believe this drop is due to a shift in the competitive metagame over time, as the LLM's training data has a fixed cutoff, affecting its decision-making despite updated statistics. We found that PokéChamp struggled against stall tactics and excessive switching, likely due to time constraints and the challenge of modeling these strategies accurately. Our analysis of these weaknesses is detailed in the appendix. During live demonstrations, we noticed that opponents aware of facing PokéChamp could exploit its excessive switching, highlighting the need for anonymity in performance assessments. Overall, our evaluation shows that PokéChamp achieves top-tier performance in Pokémon battles, surpassing both heuristic and LLM-based competitors while demonstrating expert-level play against human players. These findings emphasize the effectiveness of our approach in utilizing LLMs for complex game environments.